So today I'm going to talk about energetic particle precipitation-driven ionization and heating in the upper atmosphere of magnetized exoplanets around M dwarf. So, okay, next slide. So I'm going to discuss about why the energetic particle precipitation is important and what elements are needed in this modeling, and then what model we use. And can precipitation drive significant ionization and heating in the atmosphere? So why energetic particle precipitation is so important in the upper atmospheres of exoplanets, especially around M or K dwarf in stellar system? So they are usually so close in their host stars. For example, TRAPPIST-1b orbit is so small and so close to the host star compared to the solar system. So every planet's orbits are within the Mercury orbits. And in such a condition, the planet is under extreme stellar wind and magnetic field. The interstellar magnetic field. So this can drive extreme magnetic activity in the magnetosphere and ionosphere of planets. So this in turn can lead to energetic particle precipitation and extreme electric currents into the upper atmosphere. So energetic particle precipitation can collide with neutrals and cause impact ionization, producing secondary electrons, many secondary electrons. This ionization process can repeat multiple times until the secondary electron dissipate and become thermalized. And here at the middle, the ionospheric currents. Ionospheric currents are connected to the magnetospheric currents. Field aligned currents flow down into the ionosphere, and they connected to horizontal currents of ionosphere, which is Peterson and Hall currents. And then these currents flow back to the magnetosphere. And then since the energetic particle precipitation increase ion and electron density, it increases ionospheric conductivity, and thus more currents can flow in the ionosphere. With conductivity and currents, the ionospheric current system is like electric circuit. Thus, it can heat atmosphere through ohmic energy dissipation, referred to as Joule heating. So at the bottom, this is the example. The Cohen et al. In 2017 estimates stellar density, speed, and magnetic field, scaling solar winds, and also estimate energy dissipation from Joule heating and XUV radiation. So they show that the ohmic energy dissipation can larger up to more than 10 times. So here you can see the ohmic energy dissipation to the EUV energy dissipation. So with different conductivity value. So although further detailed calculation and simulation is required, this work shows the importance of Joule heating, and it can be comparable or even larger than XUV heating. So what elements are needed in this modeling? So to better understand, we should simulate with more realistic physics-based model. So to simulate, the model should include the following elements: the superthermal electron transport, chemistry, and conductivity, and advection. So the superthermal electron transport should be energy dependent and include the photoelectron production and secondary electron production due to impact ionization. And then those secondary electron flux or superthermal electron flux should undergo elastic and inelastic scattering. And then we should also have chemistry to get a better ion density with the production from superthermal electron transport, and then the full chemical reaction with different species. And then you should also have a module to calculate the conductivity, which is like the ionospheric Hall and Peterson conductivity calculated using the density and temperature of ion and neutrals given by magnetic field. And then to better calculate, of course, you have the time-dependent multi-dimensional multi-fluid advection, so which gives hydrodynamic and then should include heating and cooling and appropriate heat conduction too. So we recently developed Planet Eater, which is exoplanetary ionosphere and thermosphere tools for research. So Planet Eater use inputs of planet information, for example, surface density, temperature, mass, radius, and rotation period, and stellar flare spectrums, and the X-ray and UV, extreme UV. And sometimes it also requires the stellar wind parameter, and which also gives planetary magnetic field and electric currents to calculate the electron transport and conductivity, which should be provided by global magnetic field, for example, MHD model. So in the main body of exoplanet Eater, we calculate advection in 3 dimension and chemistry, and this also includes XUV heating, radiative cooling, heat conduction, and photo and impact ionization. And then, as I mentioned, we also calculate superthermal electron transport and conductivity. So the main output of Planet Eater is density, temperature, and pressure, and mass loss rate. And then on the way, we can also get the superthermal electron flux and conductivity and Joule heating rate. And this is the verification and functional test of Planet Eater. So on the left, we have the one-dimensional multi-species shock tube test. So this is actually the expected in the analytical calculation. And on the left, on the right, this is two-dimensional multi-species multi-fluid blast wave test, blast wave simulation. So on the top is calculating in the Cartesian coordinates. In the bottom is non-Cartesian spherical coordinate. As you can see, the blast wave front is propagating over time and then hit the boundary and deflect back. So this is also expected in analytical calculation. So these show that so these 3 verifications are showing demonstration that this implemented work is expected, and then this model is good to go. So the more detailed results will be presented by Alex Glosser tomorrow. So I'm not going to discuss detail here. So yeah. So the next is, can precipitation significantly drive ionization and heating in the atmospheres? So we use Planet Eater to calculate that. So we assume that the atmosphere, Earth-like atmosphere, including the molecular, atomic and molecular and ionic, oxygen, nitrogen, and hydrogen. And then we scale the precipitation from Earth's atmosphere in a moderate geomagnetic storm. For example, the precipitating mean energy is 30 kV, and then energy flux is 30 watts per meter square. Field aligned currents is 1 milliampere per meter square, which is like the 1,000 times of the Earth. So this is based on like 100 times of solar wind density and the 10 times of solar wind speed, because the exoplanets in M dwarf are so close in their host star. So that's why the solar wind, stellar wind will be much higher and gives much higher density and velocity, which drive high field aligned currents and the high precipitation flux and energy. So here show the result. So in all plots, in every plot's altitudes on x-axis. So on the upper left, we have electron energy spectrum in different altitudes. So precipitation, in this simulation, precipitation is assumed to be Maxwellian with the mean and energy flux that I showed in the previous slide. As going to the low altitude, the different color from yellow, gray, and orange to blue, there are more secondary electron production at low energy channel. So this leads to the electron and ion density increase on the right. So electron density is in the black curve, and oxygen ion density is in the yellow curve, and the molecular oxygen ion is on the red curve. So this is very significantly high density compared to the Earth atmosphere. And this in turn increase Peterson and Hall conductivity. So on the bottom left, so which is a horizontal ionospheric conductivity. So this conductivity peak at low altitude because it is a sweet spot of reach the neutrals and ion density. And then lastly, the conductivity, conductivity with electron currents can drive the Joule heating because the conductivity and electric currents acts like electric circuit, as I mentioned earlier, and give the Joule heating. So it can up to like 10 to the minus 10 erg per cubic centimeter per second. And sorry for the inconvenience. Yep, and we compare. So here we compare the
2 minutes.
Yep. So we compare this calculated density and heating rates with those in the Earth's atmosphere during a moderate storm. So for example, on the left, density can be like 5 orders of magnitude higher than the normal the Earth atmosphere during a moderate storm. And for the heating rate can be like 9 or 10 orders of magnitude higher compared to the Earth atmosphere during a moderate storm. So this result implies that energetic electron precipitation can play a critical role of exoplanetary atmosphere and their evolution. So I can summarize here. So we developed the Planet Eater, which is time-dependent 3D hydrodynamic code with heating, chemistry, and cooling and heat conduction. And density and ohmic energy dissipation, which is Joule heating, substantially increase for atmospheres of close-in, exoplanets due to extreme stellar wind conditions. So for the future work, we will couple with global MHD to get better, more physical stellar wind and XUV from stellar flare and stellar mass ejection. And we will also investigate if this can lead to the significant hydrodynamic escape, like the people simulate with XUV radiation. Thank you.
Thank you, that was great. We've got a couple of questions in the chat. So the first one is, what kind of model do you use for the superthermal electron transport?
Okay, so here actually we developed the new superthermal electron model. So we assume the steady states, and then we use inelastic and elastic cross sections and secondary electron production. So it's pretty much similar to the very famous, I don't remember the model name. Yeah, we just developed, not Giram. Yeah, Giram is atmosphere model. So I can think of
You're thinking of two streams.
Right. Two stream. Yes. Thank you, Alex.
Okay, and the next question is, do the precipitating electrons deposit their energy at an altitude where they can be effective for ion heating? At Earth, killer electron volt electrons penetrate too deeply.
So what was the question again?
So do the precipitating electrons deposit their energy at an altitude where they can be effective for ion heating?
Oh, ion heating. Okay. So we didn't particularly calculate the ion heating here. So we only calculate the neutral heating. But it's a good question. So I think the precipitating electron can also contribute the ion heating too. Yes. I mean, if density is high enough, then ion can collide with neutrals. And if the density is not high enough, then it can also, I mean, ion can collide with electrons, so it can additionally hit it by electrons too. Yes.